Reactor is critical. I repeat, W250 is critical. Just imagine being in that control room. Those were the exact, incredibly tense words spoken when a tiny team just recently made history. You know that phrase, it's the exact moment a self-sustaining nuclear chain reaction is officially achieved. But the crazy part about this specific moment isn't just the science. It's who actually pulled it off, and honestly, how unimaginably fast they did it.
Welcome back to The Explainer. Today, we are absolutely diving headfirst into a massive feat of engineering and pure ambition. We're talking about Valor Atomics. This is a startup that literally managed to build a working nuclear core, fuel it, and turn the whole thing on, all before their third birthday as a company. Think about that. In an industry where we usually measure progress in decades and billions of dollars, this team somehow did the impossible in under 3 years.
To really wrap our heads around the sheer pressure of this achievement, we have to look at the timeline. At one point, this team was sitting exactly 144 days, 6 hours, and 43 minutes away from a massive, massive deadline. Under Executive Order 1431, the U.S. government authorized 11 different teams to try and get advanced reactors to split atoms right here on American soil by July 4th. Talk about an all-out sprint against the clock.
Okay, so let's dive into this. Why was this crazy sprint even necessary in the first place? Well, right now, nuclear power accounts for about 6% of global energy generation. Just 6%! The historical bottleneck here is that it literally takes decades just to build and turn on a traditional nuclear reactor. It's this painfully slow, highly customized construction process, and that has kept that percentage artificially low, even while the energy demands of our modern world are just absolutely skyrocketing.
But Isaiah Taylor, he's the CEO and founder of Valor Atomics. He looks at that 6% and says, no way, that should be 99%. And the only way to actually hit that wild goal of powering almost the entire globe with cheap, abundant nuclear energy, we have to completely flip the script on how we build these machines. We literally have to move away from slow, bespoke construction to rapid, scalable mass manufacturing.
Section 1. The Toyota Camry of reactors, moving from construction to manufacturing.
This brilliantly illustrates the fundamental shift Valor actually made. They aren't out here trying to build a Ferrari or some hyper-complex spaceship. They're building the Toyota Camry of nuclear reactors, simple, reliable, and easily reproducible. Now, traditional reactors use water, which has a pretty massive drawback. As temperatures rise, water naturally wants to boil, right? That liquid-to-gas phase change introduces the severe risk of a steam explosion. Plus, the water itself gets radioactive. Valor's W250 design, it completely throws out the water. Instead, it relies on solid graphite and a completely stable helium noble gas, which literally eliminates that boiling risk from the get-go.
Let's briefly unpack the physics of why this specific setup gives us what's known as a walk-away safe system. First up, that solid graphite core provides massive thermal inertia and a strong negative thermal feedback. Simply put, graphite can handle incredibly high temperatures while remaining perfectly solid, so it naturally prevents meltdowns. And instead of water, Valor uses pressurized helium to carry the heat away. Because helium is a noble gas, it maintains a strictly linear relationship between temperature and pressure, so no sudden phase changes, no explosions. Plus, as that helium passes through the nuclear core, it doesn't capture neutrons. That means the working fluid itself never even becomes radioactive. It's just a brilliantly simple, fundamentally stable design.
Section 2. Building with nuclear Legos, the modular citadel.
Now, if you actually want to manufacture reactors in a factory and ship them out, you obviously need modular pieces. But that introduces a huge physics problem known as the shine path. Think of it this way. If you just stack regular concrete shielding blocks next to each other, they might look perfectly solid to us. But to a microscopic, highly dangerous gamma ray, those tiny gaps between the blocks are a straight shot right out into the environment. Gamma rays will essentially shine through any straight-line crack.
To solve this, Valor's engineers essentially invented high-tech, self-tensioning Legos. It is so cool. First, they use precast concrete modular blocks. But instead of giving them flat edges, the top and side faces are actually shaped into interlocking sine curves. So when you stack these blocks together, the curves physically block any straight line. Geometrically, that dangerous gamma radiation has literally nowhere to go. And here's the absolute best part. The way these curves are designed, the sheer weight of gravity actually pulls them tighter together. It's a fully self-tensioning, self-locking system. You just mass-produce them in a factory, ship them out, and stack them together on site.
This whole factory-built, modular approach leads to some unbelievable logistical flexes. Case in point, Operation Windlord. And yes, for all you fantasy fans out there, that is totally a nerdy Lord of the Rings reference to Gwaihir the Windlord, the giant eagle that rescued the hobbits. But in real life, this was a massive US military C-17 cargo plane successfully airlifting an actual functioning nuclear reactor.
The wildest part is that the US military has been dreaming of this exact capability since the 1960s. They actually had a program back then called Project ML1. The idea was incredibly ambitious for the time. Could you just put a nuclear reactor in the back of a plane, fly it to a remote base, and instantly have power? Well, it stalled out for decades, but Valor finally proved it's possible. Because their reactors broken down into 6 perfectly self-contained modules, they were able to load 2 modules per plane and just fly them clear across the country. It is the ultimate proof of extreme portability and rapid deployment. We're talking about taking nuclear power out of these giant multi-year construction sites and just rolling it onto the back of a standard military cargo plane.
Section 3. Splitting atoms for AI, the future of compute power.
So Valor beat that government July 4th deadline, and they took their W250 reactor critical. But they didn't just want to prove it worked in some isolated lab test. No, they wanted to show exactly what this kind of localized massive power could actually be used for in the real world. So during a live, highly anticipated demonstration, the command was given: reactor operator, raise power to 37% full power.
What happened next is honestly a game changer. The electrical current generated directly from that Valor nuclear core was fed right into a server room on the north wall. That clean, localized nuclear electricity lit up an NVIDIA Blackwell chip, which, if you know anything about hardware, is an unbelievably powerful and power-hungry piece of tech. And it successfully loaded and served a website, literally called nuclearwebsite.com, directly to the phones of everyone standing in that room.
As their CEO announced right after, this wasn't just about a startup making some nuclear electricity. This was the very first meeting of advanced nuclear generation and artificial intelligence. We are talking about pairing 2 of the most massive, world-altering forces of our time, the exponential, incredibly power-hungry growth of modern AI compute, finally meeting the clean, passive, mass-manufacturable power of advanced nuclear.
And that leaves us looking at a truly fascinating landscape. Think about it. The old rules of nuclear energy, decades of waiting, billions in custom construction, huge boiling water risks, they've essentially been completely rewritten by a startup in under 144 days of intense sprinting. So I want you to take this thought away with you today. If a dedicated team can design, manufacture, transport, and turn on a walk-away safe nuclear reactor from scratch in under 3 years, what exactly does the next decade of infinite clean power for our artificial intelligence future actually look like? That massive energy bottleneck we keep hearing about, it might just be breaking. Thanks for joining me on this explainer. And as always, keep asking the big questions.